All right, so let's start our discussion. Last time we were talking about the predictive coding. So making a precise prediction which minimizes the error between the prediction and the actual value on a time series of x of n using past samples, of course, x of n minus 1, x of n minus 2, etc. is the thing that we are trying to do. Now, we will be doing linear prediction because that is the easy one, and that's the probably most understandable one, but nonlinear prediction is also possible. It's just a little bit difficult to analyze or to make an optimization in a sense. Now, this is the first order prediction that we will start with. So the prediction value is a scale h1 of n times one past value, x of n minus 1. We're not even using x of n minus 2 and all other things, all the past. We are using just one past. So what is the optimum h1, the scale, for this kind of a linear prediction? For that, we will start by, let's turn it to black. We will start by defining a prediction error or difference d of n, which is x of n minus x hat of n, and it automatically becomes x of n minus h1 times x of n minus 1. Clearly, we cannot really minimize any random thing. We can only work on statistical parameters that are derived from this d of n, and we will therefore try to reduce its variance. We will be that will correspond to the energy of the error, and we will see that, or you can also show that this difference must be zero mean. Okay, if it is having a persistent mean, an average, then the prediction would be a biased prediction, and it cannot be the optimal prediction. So it has zero mean, therefore the variance corresponds to the energy of it. So we can write it this way. Otherwise, of course, this expected value of d square is not equal to the variance. We must subtract the mean, but the mean is zero, as I say. And that is the expected value of the square of the term x of n minus h1, x of n minus 1. So we have to take the square of it. And for that, we use algebra, of course. It is like a plus b in parentheses squared. So we start with first the first term square, x square of n, and then minus 2 times x of n times h1 x of n minus 1, okay, the multiplication, and plus h1 square x square n minus 1. So I just took the square of the inner difference or summation term. And due to the linearity of the expectation operator, we can write each individual sum or difference inside the expectation. Like we have this expected value of x square n, and the expectation parenthesis closes, and minus the terms that are not random signals, which are 2 and h1, can be taken out of the parentheses of expectation, and then the expectation starts as x of n, x of n minus 1, all right, and plus the expectation parenthesis closes, and plus, again, h1 square is not the random signal, so it can be taken out of the expectation. h1 square expected value x square n minus 1. Now, for stationary signals, uh, we will have to assume stationarity at this point, and I will also make another assumption, that is the signal itself is also zero mean. Okay, that will be an easy way of approaching the problems and showing some terminology, because if the signal is zero mean, then the correlations will be converted into covariances, and energies will be converted into variances, and variances are easier to make a representation. If it's not zero mean, what can you do? You can just subtract the mean. You can just find or estimate the mean first, and then subtract the mean from the signal, and work on that kind of a signal, zero mean signal. If it is zero mean, the first one is, which is the energy of the signal, will become the variance of the signal, assuming it's zero mean. Otherwise, you just need to write the energy anyway, and it doesn't really matter. I'm just trying to reduce the notation here. It doesn't have to be zero mean for this thing to hold. You can just find a new representation to represent the energy of the signal. You can say the energy of the signal is Rx0, by the way. That's also quite a common practice. It's just the zeroth correlation value. The zeroth covariance value is variance. The zeroth correlation value is the zeroth correlation value. You can leave it as it is. Now, here in this final part, we have the energy of the signal again. It's not x squared of n, it's x squared of n minus 1, but the signal is stationary, so it's still the same. Okay. And this one is the autocorrelation at time lag of 1. It is Rx of 1. So we could actually write it like this. You may be more comfortable with this one. The autocorrelation at time lag value of 1 is usually notated in a simpler format as the autocorrelation at value 0, which is sigma x squared, or Rx0, times some coefficient. And that coefficient is at most 1, because the autocorrelation, the relation between two signals at one sample lag is upper bounded by the autocorrelation of the signal at time lag is equal to 0. A signal is mostly correlated with itself, with no time lag. And then with a coefficient times that one, which is less than 1, it can be related to the autocorrelation at 0. And again, using the assumptions of zero means, etc., the situation actually becomes something like this. It is rho 1, that is the coefficient I'm talking about, which is less than 1, times sigma x squared. Sigma x squared is Rx0. This rho 1 is less than 1, and it must be also greater than minus 1. It cannot be more than 1 in magnitude times a version of sigma x squared. In terms of the magnitude, sigma x squared is the largest thing that you can get along the autocorrelation values for a zero mean sequence. Along the autocorrelations, it can at most be sigma x squared, and it can at least be minus sigma x squared. So rho 1 is between minus 1 and plus 1. If it is plus 1, it means, well, it is almost staying the same. Therefore, the autocorrelation, despite the time lag, the autocorrelation does not reduce. It stays constant. So it means it's a constant signal in some sort. If rho 1 is equal to 0, it means the past sample and the current sample has no correlation. The cross correlation between the time lagged version is 0, so they are orthogonal. That's also a way to visualize things, and they have no relation. If it's minus 1, it also imposes some or means a strong correlation, but in a negative way. It's negatively related. Like x of n minus 1 is a value, let's say a, then x of n is minus of a, negative of that. Whatever your past is, right now I'm the negative of it. It's becoming the negative of that. It is a negative correlation, but it's a strong correlation. It's not uncorrelatedness. All right. So rho 1 is between plus and minus 1. Now, using these terminologies, we can write the whole thing as we can put everything into a parenthesis of sigma x square. As you see, this term is sigma x square. This term is 2 times h1 times rho 1 times sigma x square. This one is h1 square times sigma x square. So let's put it in a parenthesis of sigma x square, and then it becomes 1 plus h1 square minus 2 rho h1 in parentheses times sigma x square. So this is the error that we have. Now we want to minimize this error. And how can we do that? Or with respect to what are we going to minimize? The minimization criterion is, or the optimization criterion is the filter coefficient, H1. So that is the thing that we are adjusting. What is H1, which minimizes this expression? And the way to do it is from calculus, it's quite trivial. We take the derivative of this expression with respect to the optimizing parameter, which is H1. So we will find the derivative of this expression with respect to H1. And this is the thing that we are trying to differentiate with respect to H1. So, and this must be equal to 0 at the minimum point. It could be the maximum point, but we will be finding the minimum point. So let's take the derivative of this term with respect to H1. The derivative of, we can forget about sigma x1, sigma x square. It will stay in the, after the differentiation with respect to H1, but we will say that it's equal to 0. So sigma x square will be cancelled. So what's the derivative of this expression with respect to 0? It is the derivative of h1 square with respect to h1 is 2h1. And the derivative of minus 2 rho h1 with respect to h1 is minus 2 rho. Of course, this sigma x square will stay, and this is equal to 0, which means that this is equal to 0, which means that h1 is equal to rho 1. And you can put it in a box because that is the result that we get. The optimum first order linear prediction filter coefficient h1 is equal to rho 1. You can also write it as Rx1 over Rx0 if you wish. That is the coefficient which scales sigma x1. By the way, it has a name. I didn't mention about the name, but there's a name to this. That is the correlation coefficient. This rho is known as the correlation coefficient, and rho 1 is the first correlation coefficient. So first order linear prediction is simple. It's very simply the first correlation coefficient you use. If the correlation is large, then you have a large filter value. You use a lot of information from the past data, x of n minus 1. You multiply it with a large number, the largest number being 1, by the way. And if there is no correlation between the samples, then you cannot really make a prediction just by looking at the first pass, and you multiply it by 0, for example, if there is no correlation. It means that you're not really making any kind of prediction. But yeah, we will also analyze the difference, the error that we make with this one. And as you see, as the correlation coefficient goes to 1, then sigma d square essentially goes to 0. Because just put it or substitute it here, it may be a wise idea to write that thing again. So the sigma d square is equal to 1 plus rho 1 square minus 2 rho 1, this is rho 1 by the way, times h1, which is also rho 1 sigma x square, and that is equal to 1 minus rho 1 square times sigma x square. So this is the prediction error of the first order predictor. As you see, as rho 1 approaches the value of 1, 1 minus rho 1 square will approach to 0. And interestingly, as rho 1 approaches to minus 1, again 1 minus rho 1 square approaches to 0. So that means it's a negative correlation is also a strong correlation. The only bad correlation is zero correlation, uncorrelatedness. If you have an uncorrelated sequence, you cannot make predictions from the past samples, of course. So that was the first order predictor. I will also show some preliminaries of the second order prediction, and then we will generalize. The second order prediction, I'm not even going to derive, but I will tell you what the result is. So second order prediction, it's something like this. We have a prediction x hat of n is equal to h1 x of n minus 1 plus h2 x of n minus 2. So we are using the first passed and the second passed sample. And we have now two filter coefficients. It's a second order prediction, and there are two filter coefficients. And d of n is the difference between x of n and this prediction, which is h1, sorry, x of n minus 1 minus h2 x of n minus 2. And of course, we will do the same thing. We will have to take the square of it and take the derivative according to h1 of expected value of d of n square. Take the derivative of it with respect to h1 and also with respect to h2 as well. So we will come up with two equations here. And both of them must be equal to 0. That's why I'm using partial derivatives. By the way, the square term position seems wrong. It must be like this, d square. Yeah, more like it. And the derivatives of these with respect to h1 and h2 must all be equal to 0. So we have two equations. The first one was a single equation given a single result. It was easy. Now there are two equations with two unknowns, h1 and h2, and we solve for them. And I'm just going to give you the result, and I will not continue with the derivation, because I will continue with the generalized formulation, which is actually easier to express. H1 optimum will be determined as rho 1 1 minus rho 2. What are rho 1 and rho 2? They are the first and second correlation coefficients, partial correlation coefficients. We know rho 1, but there's also rho 2, which is Rx 2 divided by Rx 0. So rho 1 is Rx 1 divided by Rx 0, and rho 2 is equal to Rx 2 over Rx 0. So it's by dividing with Rx 0, it's just like a normalization by making the variance to be equal to 1, because I am dividing everything by the variance, sigma x squared. So the correlation coefficients are between -1 and +1 always. 1 minus rho 1 square. By the way, rho 2 is not necessarily less than rho 1, but both of them are less than 1 and greater than -1. The second optimal coefficient is rho 2 minus rho 1 square divided by 1 minus rho 1 square. Now, I did this example. I show you the results of this example because of a purpose. The purpose is the following, to show that H1 optimum is not rho 1 anymore. It changes. By contributing some information from the second past data, by incorporating a new value of H2, in other words, I did something else. We did something else. And it also readjusts H1. It does not stay to be rho 1. It is updated. Now it is this value, which is clearly not equal to rho 1. It may be equal to rho 1 under certain circumstances, but it's different. So what's happening here? By the way, I want to also show you the minimized power of the difference, the error. It is now equal to 1 minus rho 1 square minus, oops, sorry, it's not sigma, it's rho 1 square minus rho 2 divided by, in the after the parenthesis there's another square, divided by 1 minus rho 1 square times sigma x square. Now I would like to compare this with this expression. It was 1 minus rho 1 square in parentheses times sigma x square. Here we have 1 minus rho 1 square times sigma x square already, but there is another term which is further subtracted. And it's a positive term which is subtracted because the numerator is squared here, and the denominator is also greater than 0, because rho 1 is less than 1, so 1 minus rho 1 square is positive. Positive over positive is positive, so this thing is also positive, which means that I'm subtracting from 1 something positive first, and then some other positive thing as well, which means I'm reducing. So this number is smaller than this number, which makes this minimized error is essentially less than the previous error, this one. This is also minimum. It is telling me that by incorporating an extra information from the past, not only the first order, but the second order past, I reduced the prediction error a little bit more. This error is, the error energy is less than the previous one. So it helps. Now, how can we generalize this thing? There are several ways for the generalization. And the generalization is, it can be considered in a way as trying to find the inverse of a system, like we have this kind of a system which makes the prediction, like x of n goes into a delay. Z to the -1 is a discrete time delay, you may remember from signals and systems or digital signal processing. And this first delayed is multiplied with a coefficient of h1, and then delayed again, which is producing the second past sample, and that one is scaled by h2, and we are accumulating these things. Again delay, and scaling with this time h3, accumulate, and it goes on like this. Maybe the last is delayed again by a delay, and then finally scaled by the last, let's say h sub n, if it is a capital N tap prediction that we are doing, and finally accumulated to make a prediction x hat of n. Okay, so this thing is therefore in a sense a filter which is acting only to the past samples. We can say that that filter is capital H, or in discrete time you can write the Fourier transform of it like this, or the Z transform as capital H of Z, whatever. And from that, the error filter that we have, which can be notated as A, is the difference between the filtered version of the input and the input itself. So we are going to say that this is an error-making filter, A of omega, or A of capital A of Z, if you write it on the Z domain, and that is 1 minus H, capital H, right? This is an error filter. The input is X, the output is the prediction error. That is A. And this A filter, if you apply this filter to the input, must make the output to be uncorrelated. And the most uncorrelated signal that you can obtain is the white noise. So it is sometimes known as a whitening filter. So the input is becoming white noise at the output. The input is whatever it is. The input has the power spectral density, let's say, as S sub X. So this is the power spectral density, which is the Fourier transform of the autocorrelation of X. And you filter this using this A, you filter this signal using this A, which means you are multiplying the power spectral density with the magnitude square of A. And you are trying to come up with 1, which is the power spectral density of white noise. So A is trying to do this, which will tell you that you are trying to, in a sense, you are trying to make this A, at least in magnitude square, as close as possible to 1 over Sx of e to the j omega. This is something that you're trying to make. You are trying to invert the power spectral density of the input as this whitening or noise generating filter. But this is too abstract. This kind of an expression of trying to find an A, and then from that A is 1 minus H. So trying to find h from there. This is too abstract, okay? But I want to show you from a different perspective how these can be attacked. By the way, using digital signal processing knowledge, if you can come up with this expression, this is a magnitude square, which means it is a times a conjugate, because a times a conjugate is a magnitude square. So you cannot really resolve which parts of the filter corresponds to a and which parts correspond to a conjugate. It's known as pole zero factorization. You know the magnitude square, but you don't know itself. Uh, there are several techniques to resolve for the individual a inside, like the minimum phase solution. It means both the poles and the zeros are chosen to be inside the unit circle, and the conjugates are the ones that are with poles and zeros outside the unit circle, in case they are in the reciprocal inside and outside pairs, which must be because it's a magnitude square term. But I have already talked too much about this information, which we're not going to use. But I wanted to talk about these regarding the significance or the importance of signal processing, signal sense systems, and digital signal processing. So that kind of an a priori information is quite critical in all these disciplines. Although we are trying to do compression here, as you see, some deep diving signal processing concepts came into the picture. Now I will continue from here on. I will continue with the linear predictors again. And I will talk about the minimization of this expression, which is the expected value of d square, which is the expected value of x minus x hat square. And at this point, I will write it in a generalized form, like expected value of x of n, in a parentheses, of course, minus a linear prediction version, like from j from 1 to capital N, h of j, x of n minus j. So this is the linear predictor that I'm applying, and the difference square is put inside an expectation operator. So we will continue from here, and this thing will be used for the optimization. How? We will take this and take the derivative of this expression with respect to all hj's, j from 1 to capital N, like this, sigma d squared del hj. And they must all be equal to 0 for j from 1 to capital N. Now, therefore, I need to find the derivative of this expression with respect to an hj in between. Let's find one case of that. And when we do that, or how can we do that? There is a square term here, and inside it we have this hj. So how do we take the derivative with respect to hj here? We have to use the chain rule for differentiation. This derivative must be equal to, staying inside expected value still, a large parenthesis of expectations. Because of the square, it becomes 2 times x of n minus x hat of n. I will write because it's easier. Although we know what x hat of n is, x hat of n is this one. Or you can write it explicitly if you wish. And then the derivative of that x hat of n with respect to hj. That is the chain rule for differentiation. And yeah, we can close the parentheses. So now we have to evaluate this or proceed from here. I want to start from this part. What is the derivative of the prediction? The prediction is this with respect to hj for a j. It's not a running index anymore. We choose one of them, one of those hj's. And when you choose that hj, you notice that it is multiplied by xn minus j. For example, let's say it is h3 times xn minus 3. What is h3 times xn minus 3 derivative with respect to h3? It is xn minus 3. So for every j, the derivative of this expression is essentially xn minus j. So this is essentially x n minus j. Okay. So in the chain rule, outside this parentheses, we have here actually xn minus j instead of this. And inside, we still have this expression. So let's write it in that way. That is, this one is equal to expectation of xn minus x hat of n times x n minus j. And this is equal to 0. You may ask for what happened to this 2, but it is equal to 0. Therefore, 2 is just cancelled. The inside must be equal to 0. 2 can be taken out and it's equal to 0. So inside the expectation, we are left with this one. There is an alternative way of writing this, which is even shorter. The first part is xn minus x hat of n is, as we know, it's the error, d, times x n minus j is equal to 0. But when we write it like this, there is a way to translate this thing. It's an important result. It is telling me that the the prediction error, d, is orthogonal to the past samples. So using past samples, we cannot make a prediction which has some residual information remaining from the past samples. Okay, it must be orthogonal. That is also known as the orthogonality principle. But I will continue. I just made a pause here, a small pause, to show that the prediction error is orthogonal to the past samples, and it's important. But now I have to write the prediction error in an explicit form to see further what's happening. Again, x of n minus x hat of n, but x hat of n is, as we know, it's j from 1 to capital N, h of j, x of n minus j, and let me close the parentheses, times x n minus, I seem to make a confusion here. Let me change one of the variables, either x of n minus j or the summation j. Let me change this one and I make it I, which will give me, by the way, this is for all I, which will give me an optimization criteria for the ith coefficient, hi. This will help me solve hi. if I use j here, it will be confused with this j, which was the running index. It's a different thing, so I'm using a different parameter for that. Let's say I. So from here, I will solve for hi. But what is this inside the expectation? Now, a closed inspection shows that this is x of n times x of n minus I minus this times x of n minus I. I will write it a little bit in more detail like this. Expectation x of n minus I is one thing here, and minus the summation I'm going to take out of the expectation, because expectation is a linear operator and summation is also a linear operator. See what I'm doing. Be careful and closely inspect what I'm doing. Summation j from 1 to n. So I didn't put the expectation out of it. I'm pushing the expected operator inside the summation. And I'm also taking this hj out of the expectation operator too, because it's the coefficient. Expectation is now starting. And inside we have the random signal, n minus j times x of n minus I. Okay, this is equal to 0, again for all I. Okay, if this is equal to 0, if this difference is equal to 0, this minus this, then this must be equal to this. All right, that is the way that we can solve for it. But before that, I'm going to write their shortcuts. What is expected value of x of n times x of n minus I? It is Rx of I, okay? And minus is equal to 0 means it is equal to now the right-hand side of the equation, which was here. And what is that? It is summation j from 1 to n hj. What is expected value of x n minus j times x n minus I? It's again an autocorrelation. What is the time difference between n minus j and n minus I? It is I minus j. Rx I minus j. Again, for all I. And j from 1 to n. For all I mean I from 1 to n, capital N as well. All right, so this is it. We found it. You may be aware of the solution or you may not be, but we essentially found these coefficients, or we can find these coefficients by solving this set of equations. How many equations are there? There are 1 to capital N, so there are capital N linear equations. If you know Rx of I minus j, of course, or Rx of I for all the necessary coefficients, what are they? Let me write it, let me put it in a more explicit format so you may understand hopefully better. It's like this. Here, the left-hand side of the equation is Rx of I for all I, which means like Rx of 1, Rx of 2, all the way up to Rx of capital N in a vector form. I can write the set of equations in a vector matrix multiplication format, in other words. So the left-hand side of the equation is consisting of Rx values for all I from 1 to capital N. And the right-hand side is essentially a matrix consisting of Rx of I minus j. When j is equal to I, it becomes Rx of 0. When I is 1 more than j, then it becomes Rx of 1. and it goes all the way up to Rx of capital N minus 1, not up to capital N. And here it is Rx of minus 1, but it's equal to Rx of minus 1 is equal to Rx of 1. And this is Rx of 0 all the way up to Rx of N minus 2. And these rows go all the way up to Rx of N minus 1, Rx of N minus 2, down to Rx of 0. So in this matrix, you notice that the diagonal is Rx of 0, and the off diagonals are Rx of 1s, Rx of 2s, and the corner points are Rx of N minus 1. And the thing that multiplies these are h of j's, which can be considered as h1, which is optimized, h2, which is optimized, and finally hn, which is optimized, like this. And h1 up to h capital N are the things, the filter coefficients that we are trying to find, right? How can we write them in a more compact way? It's like this left-hand side is a vector, let's call it an Rx vector, is equal to a matrix, let's call it an capital Rx matrix, times another vector, which is the optimum H vector. And from here, we know that in order to find H, all you have to do is invert the matrix and multiply it with the left-hand side vector. And that's it. Rx, the autocorrelation matrix inverse times the autocorrelation vector. Now, it looks very simple, and it is indeed very simple. It only has some technical difficulties for the evaluation, particularly for the old computers. If you're looking for a long linear prediction, like 100 tap linear prediction, it becomes the inversion of a 100 by 100 matrix of Rx, which may be troublesome for small memory, such things. So technically, it's a little bit difficult, but mathematically, the problem is solved. It's this. You may be curious about whether if this is the case or it really works for the previous solutions, and I recommend that you check it. I will show it for H1 only. If you check it for H1, in the case of H1, the left-hand side becomes Rx1, which is just one, a vector with only one element, which is a scalar. And the right-hand side is a matrix which with only one coefficient, which is a scalar, times here we have a vector with only one coefficient, which is h1, like this. So h1 is quite simply equal to rx1 over rx0, which was the solution that we have already found. So it obeys the results. Our previous two examples were just examples of this general form. And as an exercise, I may request you to also verify the results of second order equations. Where are they? Yeah, they are here. These ones. Whether to see whether they are indeed the solutions of these optimized filter coefficients. And you will see that, of course, they correspond to that. And this division by 1 minus rho 1 square, etc., it's just a discriminant of the linear algebra in inversion. You will see that if you make the exercise that I suggest. And then it may be also of importance to analyze what is happening to the prediction error, because we are doing the prediction to reduce the prediction error, right? That was the whole idea of the compression, to reduce the energy of the prediction error in such a way that it will help us for our compression purposes. So let's see what is happening to this. It's clearly equal to the square energy, which is also the difference between x of n and x hat optimum of n squared. And from the orthogonality principle, we can write something like this. One of them is, I will leave one of them as d, and not with a square, but with d of n, and the other one as x of n minus x hat optimum of n, okay, like this. So I'm using half from the first side and half from the other side in terms of the multiplication square terms. And from the, maybe before that, I will continue from here. I will multiply, I will explicitly open or extend the square term like this. Xn times xn minus x hat optimum of n is one term, and minus expected value of x hat optimum of n times xn minus x hat optimum of n. Okay, so this is the first thing that I want to write it as. And using this kind of an extension or expansion, and using the orthogonality principle that I have just introduced you with, which is telling me that this is essentially zero, because x hat optimum is this thing, x hat optimum, must be orthogonal to the error. Why is that? This is the error. This is the error. And we know that error values, dn, values are orthogonal to x of n minus I, like x of n minus 1. It is orthogonal to x of n minus 1. It's also orthogonal to x of n minus 2, x of n minus 3. All the past samples are orthogonal to the error. You remember that? How about this one, x hat optimum? It is a linear combination of those past samples. So this is consisting of past samples. It's an ensemble of those past samples. And this is an error. And each of these past samples are orthogonal to this error. So the combination of those past samples are also orthogonal to the error, okay? So this being zero comes from, again, the orthogonality principle. And therefore, we are left with this part only. This part remains. And since that is the only thing that is remaining, we can now expand it to become expected value of x square of n, okay, minus expected value of x of n times x hat of n. The second one is optimized. And that is equal to sigma x square minus expected value of x of n, x hat optimum of n. This is the minimum error energy that we have. As you see, it is clearly less than sigma x square. And by the way, we can also write the same thing in terms of the autocorrelations. Of course, we can continue writing this in terms of the autocorrelations. It's equal to sigma x square minus, I will expand this thing into the summation formula that we have used, and using the expected value and multiplication with x of n, after that taking the expected value, will give you this kind of a summation. Let's say I from 1 to capital N, hi optimum times rx of I. I omit the steps from here to here, but it's quite clear. If you just expand the formula of x optimum hat of n in the form of summation and multiply it with x of n and then apply the expectation operator, you will definitely come up with this expression, which can further be written in a form of vector multiplications, like h optimum vector transpose times the rx vector, like this. It can be written. And the h optimum, here, look at what it was. H optimum is Rx inverse times Rx. So I will substitute that information into here. And finally, we come up with the result of sigma x squared minus Rx transpose times capital Rx inverse times Rx. Now, as you see, this thing is subtracting something from sigma x squared, and that something, is it positive? If it is positive, then it means this prediction error energy is less than the signal energy, if this is positive. And that's the whole point. We are trying to reduce the energy. And is this thing therefore positive because we are subtracting that? And the answer is a clear yes. Because of the symmetry, or the transpose is equal to the same thing, structure of Rx. Rx inverse is also symmetric matrix. And multiplying from the left-hand side with the transpose of a vector and from the right-hand side with the vector itself will make certainly a positive value inside after this expression. It will give you a scalar, and that scalar is certainly positive. So we subtract a positive thing from sigma x squared, therefore sigma x squared value is reduced to become the prediction error energy, sigma d minimum square. So these are the things that we will have to remember when we are applying linear prediction. It reduces the energy or the power, more like power, because these are power signals. Random signals are power signals for being stationary. And it also, and the corresponding filter coefficients are given like this. These two are the important and significant formulas that we have to keep in mind. Now, we will give some amount of break, and after the break, we will continue with the following discussion. We will try to visualize, geometrically visualize the prediction error power, sigma d square, as a surface with axis of h1 versus h2 if it is two-dimensional, or if it is multiple dimensional, then it's a hypersurface. So how does it get minimized? In two dimensions, it must become a paraboloid sort of thing, and the minimum point is found for the sigma d square. And that minimum will give you the optimum points of h1 and h2 axis. We will visualize that one. We will start by doing this analysis, and then we will continue briefly with a way to solve this equation, which I claimed to be difficult. But I have to confess now that for today's computers, maybe 100 by 100 matrix inversion is a piece of cake, and it's not very difficult. But it was difficult, and for those difficult times, we used to have some way, some iterative way to solve this equation without inverting the matrix. It's a numerical method that we will see. I'm not going to show the derivation. I will just give you the hints, and I will give you the numerical iterative algorithm. And that algorithm also, it will give an answer to the following question. So for first order prediction, this is the prediction error, and this is the prediction filter coefficients. For second order, this is the error, these are the coefficients. For third order, this is the error, these are the coefficients. But we don't really know what kind of prediction order we will apply beforehand. So what is the correct prediction order then? I'm going to give you a set of signals, signal values, and you don't know which prediction order to apply. So what's the optimum prediction order? That's a question. That iterative method not only gives you a method to solve this equation for a given size, prediction filter size, but since it will be growing gradually, you will be gradually monitoring the error. The error will decrease, and after some time it will not continue decreasing, and you will stop there and you will say that, okay, this must be the prediction filter order, which is related with the statistical properties of the signal. How many backwards is it related with? Is it only an autoregressive 1 sequence? Is it an autoregressive 2 sequence? Is it an autoregressive 3 sequence? We don't know which one. So the algorithm will help you to monitor and decide what kind of an autoregressive signal it really corresponds to, and it will help you stop at the point where it does not contribute any further. And we will see all of these. Right now, I can see that it's a little bit past, half past 10. So let's meet at 11 o'clock. Oops, sorry. Meet at 11 o'clock, and we will continue. By the way, if you have any questions, if you come up with any questions, then please formulate those questions, and in the beginning of the next hour, you can ask them before we start, okay? So right now, I will end the meeting at the same place we are meeting at 11 o'clock. See you.